Okay, thank you for waiting. Had a little bit of technical difficulty. Okay, well, today we'll continue our discussion about the property of autoregressive model. And let's start with, it's done. Done. Thank you. We've seen this one, autoregressive process of order 1 in this form. So right hand side of this equation, we have only one leg. And we know that, but actually we assume that ET, random disturbances, they are identically independently distributed random variable with two known moments, expectation and its variance. When we say identical, that means all these sequences have same expectation and constant variance. In essence, it's identical. Otherwise, it's going to be heteroscedastic. Okay? Independently distributed, that means the value of ET doesn't depend upon previous outcomes, ET minus 1, T minus 2, and so on. Okay? So that's all we assume. Here's a new one. Well, this is usually imposed. The absolute value of parameter, pi 1 in this case, only parameter other than sigma squared, is bounded by this quantity, 1. Okay? So pi 1 is greater than minus 1, but less than 1. That's one of the conditions. We will call it as a stationarity condition, which I will explain shortly. This notation, this representation can be rewritten in several different forms, where you bring this term to the left-hand side, factor this out using lag operator L, and also you know that notice that this part is function of lag operator. Okay, so simple notation. Okay, suppose that this is very small number. Just I'm making it up. Very small number. Suppose this condition is not met. So suppose pi 1 is, let's say, 2. Then what happened to the time path of x? Or is it likely to happen? It will continue to grow, right? So it won't be, it's less likely that it will return to its mean, right? So we try to avoid that kind of situation because we don't see that kind of thing happen often. So when we talk about stationary autoregressive process, then we usually impose this restriction, but the general statement is like this. In order to check whether a particular process is stationary or not, we calculate this one. First, we look at this part. So 1 minus pi 1 L. Okay? Treat this part as unknown. So let's denote it by Z. Okay? And then take determinant, absolute value in this case, because it's a scalar polynomial. And the condition says, actually this is known from the properties of difference equation. This process won't be exploding if the root, there's one root, which is a solution of this equation for Z. The root lies outside, let's say, unit circle. When I say complex unit circle, a complex number is expressed in this way, right? So this is the real part, imaginary part. So let's say this is real part, this axis, and this is imaginary part. When I say unit circle, you're looking at unity, the length. You connect this one. So the radius, which is this distance, is always 1. So this is unit circle. Because there will be only one solution to this problem, which is z equals to 1 over absolute value of pi 1. Right? And pi's are usually a real number. So that number, if that solution, z, lies outside this unit circle. So this is on the unit circle. This is outside the unit circle. This is on the unit circle. This is outside the unit circle. Okay. So if this number is, let's say, pi 1 equals to 0.9, then z is going to be greater than 1. Okay. If this is greater than 1, absolute value of pi 1 has to be less than 1. Same thing. Right? If that happens, it's guaranteed that the process X won't be exploded. It will revert to mean. Okay. Okay. So there is one. The second one. Well, suppose the root turns out to be 1. In our application, sometimes we are interested in whether a particular process have a root that is 1. So if a particular process have a root 1, we say that's a unit root process. In this equation, when pi 1 is 1, this equation becomes x of t equals to xt minus 1 plus et. If that is the case, later we can see easily that that kind of process won't be having constant variance over time. So time dependent, which violates stationarity condition. Okay. So let's take a look at more closely some technical, a few technical things. If stationarity condition is met, xt process will vary around the mean and revert toward mean if it happened to be away from mean. Okay. And in the previous case representation, I intentionally set the average value, the value it tried to revert in the long run, that is set to 0. So to see algebraically what is, let's say, the mean and the variance of AR1 process, I rewrote previous representation in this way. So previously we had this part multiplied on the right and left hand side, right? So we are treating this one as if it's a number. So we divide that both sides by this quantity, right? So this is the equation. Well, usually we cannot do that. We cannot write this one to this one unless this condition is met. So if that condition is met, this is the case. If you try to recall what you learned from high school, this expression appears very familiar. Like this is like 1 over 1 minus pi 1L. Okay? Suppose this absolute value of this one is less than 1. Then we can rewrite this part as this infinite sum. See? Well, the factor is, of course, this guy. Pi 1L squared and cubed and so on. Okay. And we know that if you want to sum this one over to get this result, this factor pi 1L has to be less than 1. Right? So implicitly, what we are saying is, of course, this one is less than 1 in absolute value, and also determinant of L, or absolute value of L, is also less than 1. Okay. If you rewrite this one to that, and also you can expand it, right? So I rewrite this one as ET pi 1 ET minus 1, pi 1 squared ET minus 2, and so on, right? Infinite sum. Or sometimes you can use this summation sign. So when j equals to 0, j count equals 0, pi 0, which is 1, et, right? So this when j counter is 1 and pi to the power j and et minus 1, which is this one, and so on, right? So several different ways of writing AR1 process. Right? Some short notation using summation sign, some infinite sum this way, or short notation this way, or the other way around. Okay? The reason why we rewrite stationary AR1 process in this way is to calculate, for instance, expected value. If you started with this one, what is the expected value of xt? Of course, that's the expected value of that, right? Then what is that? We don't know, right? You're interested in what is the expected value of xt? Now your answer is expected value of this guy and that guy. Right? So you don't get answer, right? So you are not applying expectation operator directly to this one. Instead, you're applying that to this one. Now, expected value of x, which is the left-hand side. What is the expected value of right-hand side? 0. Right? If k is constant, some random variable, expected value is k times expected value of random variable, right? And we assume this one is 0, so 0. Last time I mentioned that the constant is by definition not a random variable. So we don't calculate expectation on random variable. Oh, sorry, constant. Okay. Expectation is calculated for random variable because the outcome is going to be uncertain, right? But when you calculate expectation this is random variable, but when you actually calculate expectation, the result is constant. Right? In this case, 0. Okay. That's a simple statement, but sometimes people forget. Later, we'll get back to this point again. So in this case, anyway, we calculated expected value of that as 0. How about the variance? Now we can apply variance formula to this one. Okay. Variance of some constant times random variable. So you are with me, right? So this is the variance operator. Usually in high school, you go from here to there directly, right? But I wrote it in this funny way. The reason being that E of t, in this case, is a scalar random variable, a single variable. But sometimes it could be vector. Vector, more than one variable. In that case, this is going to be replaced by not a single parameter like this one, instead covariance matrix. Okay. And then in this case, this is going to be a vector. Sometimes column vector, row vector. Okay. So this is more general notation. Okay, so having that in mind, now you can calculate the variance. Because this is identically distributed, so covariance terms are all 0. Okay. So actually, we are not worrying about covariance between these numbers. Okay? That's by definition, E of t is independently distributed. Okay? So we apply this variance formula to each and every element. So this one, sigma squared, this one squared, and the variance is the same because it's a stationary process, and to the power 4, and so on. Okay? Now, because the absolute value of this one is less than 1, now we can sum it over. Well, when you see this one, later I'll ask the same question, but we can do it here. Sigma squared is the dispersion measure for ET, which is a disturbance term of AR1 process, right? So sigma squared will determine the dispersion, the range where it varies, right? And then x of t was on the left-hand side, right? Now, the variance of this one is in general, if x of t is stationary, so that the absolute value of pi 1 is less than 1, this number will be in general greater than sigma squared. So, for instance, E of t varies within this region, for instance. X of t could vary in a wider range. So this expression shows what happens. Okay. What happens if pi 1 equals to 1? It has a unit root. This is 1. As pi 1 approaches to 1, well, it's not going to be defined, right? So the finite moment doesn't exist. So that's the reason why we are stating a condition where this part is excluded and looking at that direction. That direction is stationary condition. Okay. Before we move to covariance, the expectation and the variance we calculated in this exercise, more accurate term that is unconditional expectation and unconditional variance, which means if you have wrong data, then the expectation and variance refers to the sample average of everything. So, so this one and that one both are unconditional moments. But when we discuss later the forecast of xt and also the volatility of x, then we'll have to think about what is conditional expectation of this model. So we try to distinguish unconditional moments versus conditional moments. But when you have a sample, the data, and if you calculate sample mean and the sample variance, and those are counterpart of this unconditional mean and unconditional variance. Just your sample is small, you are not using whole sample, right? From minus infinity to infinity. Right? Okay. We'll calculate this theoretical correlation function for this AR1 process only, because the rest of the logic is very similar, but computationally is messy. But you can see that how we calculate, let's say, covariance of AR1 process and autocorrelation of AR1 process, so that hopefully we can extend this method to calculate ARP and even more general model like AR, MA, PQ model. Okay. Covariance between two observations, k period apart, is defined as a expectation or sample average of what? Two cross products, right? So one x of t, the other one xt minus k. And the expectation are the same because it's stationary, because we assume that, right? In our case, expectation was 0, right? So we don't have to worry about these two. Just take cross product and take the average, and they'll give you covariance, right? But let's try to calculate theoretical covariance. Well, this xt minus k is right there, the same thing. But I wrote this one in this way. How do I get this one? We did that exercise before. You lag both sides by 1 period. So t minus 1, t minus 2, t minus 1, right? And plug that into t minus 1. Okay. Then you will end up with some term with xt minus 2. Lag this one twice, 2 times. And then plug that in. And you can continuously, you can repeat that process. And you end up, if you repeat that k times, this is what you get. Okay? This is what you get. Now try to calculate expectation of the product of this and that. The first part is easy. You see, pi, which is parameter, this one, right? To the power k, and xt minus k, xt minus k. xt minus k, xt minus k, which is gamma 0, right? The variance, right? So variance times this one. How about second term? Second term. Actually, we can, if you continue to continue this kind of process all the way up to infinity, xt minus k can be rewritten in this form. Okay. So now, because you already calculated expectation for this product there, how about this product? What is the expectation of this one? But as you can see, this part and this part, which is the same as this one, has no overlap, right? Because here is a combination of, sorry, this has to be ET, sorry. Yeah, notation has to be this one, ET, ET. Okay? This ET sequence runs from T to T minus K plus 1. Right? And this one runs from T minus K to the past. Right? So if you multiply, you try to multiply this lengthy thing and this K thing, there is no overlap, right, in terms of subscript. Because we assumed it is identical series, independent random variable, E of t. So the cross product between these will be all 0. So plus 0. Okay? So gamma of k is computed this way. So if k happen to be 1, xt, t minus 1, the answer is pi rho 0. And gamma 2, pi squared, gamma 0, and so on. Okay? So that's the covariance. You can calculate easily this variance. And if you happen to know what is the value of AR1 coefficient pi, then you can calculate this one. Okay? What is the autocorrelation? We know that autocorrelation is scaled covariance, scaled by variance. Right? So this divided by variance, so this cancels out. So pi of k. So again, going back to previous example, let's say pi 1 equals to 0.9. If x of t process is generated from AR1 with coefficient 0.9, then theoretical autocorrelation function at lag 1 has to be 0.9. And at lag 2, 0.9 squared. At lag 3, 0.9 cubed. So it's going to be declining exponentially. Exponentially. So I summarize it here because you're actually plotting this pi of k over k if pi 1 turns out to be 0.9 at 1, and it will decline like that. So we say autocorrelation function is tapering off. Okay. But we learned previously when we talk about partial autocorrelation. Partial autocorrelation of AR1 process will cut off after lag 1 if true process is AR1. Right? If true process is AR2, it will cut off after 2 lags. Right? And if AR3 process, partial autocorrelation will cut off after lag 3. But here, the autocorrelation function, whether it declines this way, or let's say if this is minus 0.9, minus 0.9, 0.81, it oscillates, right? But still tapering off, right? Still tapering off. Also, if it is AR2 and stationary, it could have more complex dynamics for the autocorrelation function. But the feature is it's going to be dying off. Okay. And PACF, that will cut off. Okay. So, because we've calculated theoretical autocorrelation function and partial autocorrelation function for, let's say, AR1, and because we found this type of feature, so if you have particular data, let's say price earnings ratio, then if it is really close to AR1 process, then you are likely to see from a sample that partial autocorrelation will cut off after lag 1, and autocorrelation function will die off. Simple? Confusing? Okay. Okay, you are still with me. Okay, seeing is believing. I tried to simulate AR1 process about 300 observations. Simulation is not going to be that difficult. Because you know that, let's say, x of t, it has structure like that, right? So let's say we don't know whether ET is generated from particular distribution, but you can make an assumption, right? So suppose you are making an assumption that E of t is generated from standard normal distribution. Okay. So you assume, let's say, x of 0 is started from value 0. Okay. And what is x1? Assume pi 1 is 0.9. 0 times 0.9 plus draw one number from distribution. And that's going to be one candidate for x of t at 1, right? So some value. So accidentally, this number drawn was 0.252. Okay? And x1 is plugged in times 0.9 plus draw another number, and you'll get that, right? So you can sequentially draw this path. So this is one of the paths. By just looking at this graph, can you tell whether it is generated from AR1, AR2, or AR3? or ARMA, some combination, P and Q. Very difficult, right? But intentionally, I generate this particular realization for x sub t, assuming some big value, closer to 1. Okay? So what's really going on here is, because I assumed mu, potentially sample mean of this one, 0. So 0 is the long average, unconditional mean of this process. So sometimes it is away from 0, right? But it will revert. Why this happen? Well, sometimes this could be negative, right? Some big negative is built and pushing this thing downward, right? So if you pick several ET negative, then it will return to mean, right? And then in this case, if it's too small or too far away from average, then it start revert, right? So it has that kind of feature. To see whether, in fact, well, just seeing this one, if I just insist, well, this is stock price of Samsung Electronics, hiding this axis and that. Well, very difficult to argue, because you don't know real property of this sequence, right? But applying the concept of autocorrelation function and partial autocorrelation function will give you some clue. So the first one, this one, is using this 300 observation as a data. I calculated autocorrelation function. So sample autocorrelation function at lag 1, because this is 0, 1, 2, 3, 4, 5. Well, here at 0, 0 means rho 0 is simply gamma 0 divided by gamma 0, which is 1, right? So this is 1. And 1, this value, is lying between 0.8 and 1, right? Less than 1, right? So some number, it could be like 0.9 or 0.95. And then it shows the future. It's tapering off. Right? How about partial autocorrelation? Partial autocorrelation says this is lag 0, lag 1 here, lag 1, 2, 3, 4, 5. Okay. And lag 1, this is that. And then this is the band, the second one, second lag, third lag, and fourth lag, and so on. Or statistically, 0, right? So what happened to what the information these two graphs show? Partial autocorrelation cuts off after lag 1, right? And autocorrelation function taper off. So it's the best candidate model for this if you've seen these two information, AR1 process. Right? AR1 process. Yes?
Where this pi1 is equal to 0?
Pi1 equal to 0. Yeah, that means x of t is simply random number. E of t.
So what would be the behavior of this autocorrelation function?
Theoretically, it's all 0. It's tapering off, and 0 is one of them, right? Flat curve is one of them, right? That's extreme case. It's tapering off this way. So actually, if pi 1 is 0, then it's going to be just purely random a variable e of t, x of t equals to e of t. So there's no significant partial correlation and sample correlation, right? Anyway, right? So you can easily see that. And I show the example of that kind of thing. Any other question? Okay. In fact, if pi 1 is not 0, whether it's positive or negative, but less than 0, greater than minus 1, now you can tell the answer to this question. Will this hold? Answer is yes or no? It's 50-50. Toss your coin. This holds? True. Right? True. Okay. But when you actually rewrite x of t in this way, as before, we know that we can expand this one as an infinite sum, right? So we'll have et and many legs of, infinite legs of e of t, right? That posed quite interesting observation that, well, you see many real life data, x, but that is modeled by something that doesn't contain any information. So we called it white noise, right? That disturbance term, we called it white noise. But in somehow, if you are calculating some linear combination of all these e of t, then you can describe dynamics of x of t you observed. So it's like e of t is just a piece of Lego. Your cousins play with Lego, right? Just simple squares, right? But when you add them up, you can make a lot of things. Dinosaur, airplane, ships. Right? So time series model is not that difficult, but the structure is quite amazing. Very simple, but it's very flexible. So if you have e of t sequence, and if you want to generate something like AR1 process, what it tells you is that if you define those coefficients in this fashion, these weights in this fashion, that will make AR1 process. For AR2 process, those weights are going to be different, but the structure is about the same. AR3 process can be expressed in terms of all those stationary random disturbance terms, but with different weights. So in fact, any stationary time series can be written in this form. So let's say, just use general notation, psi. So psi 0, by definition is set to 1. Psi 1, psi 2, psi 3, psi 4, and so on. So if you set psi 1 as pi of 1, psi 2 as pi 1 squared, psi 3 as this one, and so on, that will generate AR1. If you write those psi's differently, then you have different time series model. Well, suppose that this psi 1 is not 0, but rest of psi's are all 0. Suppose you set your model in that way. What is this model? That's MA1, moving average process of order 1. See? So every stationary process can be represented as this infinite weighted average of disturbance terms. Suppose you have a non-zero average or unconditional mean of x of t process. The way you can write is this way. Deviation from mean follows autoregressive process. Deviation from sample mean is that. Can I rewrite that as x of t equals to 1 minus pi 1 mu plus pi 1 xt minus 1 plus e of t? Can I rewrite this way? I can do it, right? So you're with me? Okay. So this is parameter, actually product of parameters. And the parameter. The way we estimate actually this one using real data and using method least squares, xt minus 1, x of t. Suppose you plotted them here, scatter diagram. Suppose numbers turns out to be this way. Estimating pi 1 parameter using least square amounts to finding intercept term and the slope, where slope happens to be this number, and the intercept term is this number. Okay. So if you're using software, statistical package, and instructed to find, let's say, what is this one and that one, by saying, well, it has this one as dependent variable, and this one as independent variable. It's a linear model, and it has intercept term and slope coefficient. Then usually what you find is the answer will be pi 1 hat, and this number, which is this whole thing. Of course, you know this number, so you can recover mu. The reason why I write this one in this way is, well, if you actually calculate expectation of x of t, this guy, using our previous procedure, expected value is going to be mu. So average value. Okay. But if you run a regression of x of t on xt minus 1 and constant, this number is not going to be your unconditional mean. It's this product. Okay. So sometimes you are just interested in this coefficient. Then it's okay whether you estimate in this way or the other way around. But if you are interested in what is the average value you try to return to, then you have to specify differently. Okay? But let me show you that here. In EBUS, least square price earnings ratio, let's say this is the name of variable, x of t, include constant and AR1. Then EBUS will return this number, pi 1, which is the coefficient to the AR1 part, and other coefficient for this C, constant, which is this number. Instead, if you run a regression of this one on constant, and in EBUS, this is the notation for lag 1. Okay? A lag 1, then this number is returned, which is this number. Okay? So, S&P 500 data, the price earnings ratio, it says PE was dependent variable with sample size, mine in this example from 1873 to 1997. And it says variable AR1 and C, right? So when it says AR1, then it means that the C corresponds to mu, long average. So 14% is about long average S&P ratio. And AR1 coefficient turned out to be 0.95. So absolute value is less than 1, right? Satisfying our condition for stationarity. Well, the variation of this one, so this is annual S&P P ratio, is explained about 35% by previous period, previous observations. So fairly large. The other one, it says inverted AR roots. We say for stationarity, we say the root has to be greater than 1, right? Greater than 1 or less than -1, right? But it says, well, if you calculate AR roots, then this number, this is the value Z. You calculate it, assuming pi 1 is 0.95. If this is that, but it says it's inverted. So it's inversion. So if something is 1 over that, right? So it has to be less than 1 in this case. I don't know why EBUS tried to do this, probably to confuse you. But so you can think of this one as the other way around. So what has to be greater than or equal to 1, in this case, it is expressed the opposite. So it has to be lying within unit circle. Okay? So 0.60 is less than 1. So it is stationary process. And obviously, we can tell that by just looking at this one, because we know condition absolute value of pi is less than 1 is a stationary condition. Okay? Let's take a little more of other general model and Then we get to our examples. Okay, AR2 process, you have lag 2. So nothing fancy. Stationarity condition. It says if all roots of this one, so that's polynomial of second order, right? So it has z and z squared. And the determinant equals to 0. And the roots, how many roots in the second order equation? 2 roots, right? 2 roots. Because if you have 2 roots, then there is a possibility that 2 roots are all containing imaginary part. Right? Then in that case, you have to check whether 2 roots lie outside this unit circle, or we call it complex unit circle. So if one root lie there, the other roots lie here. How to calculate this length, showing it is greater than 1? Right? So it's going to be that. And the other case, this is minus b. So you can actually check, after calculating actual number, z, 2 roots, 1, let's say a plus bi, b minus a minus bi, 2 roots, then you can figure out whether it's greater than 1. Or if we convert this statement to more familiar space, like 2-parameter space, where pi 1 and pi 2 lies here. Okay, there are regions where the stationarity conditions are met. So rule of thumb is if 2 parameters are summed and it's less than 1, usually is more likely to lie this outside region. Okay. Also, second condition and third condition, probably you don't remember, right? It looks, very, very complicated. So usually we don't check this condition. But first condition is usually checked as a rule of thumb. So if AR1 coefficient or AR2 two coefficients are summed to 1, then that's non-stationary. If greater than 1, it's non-stationary. So suppose this turns out to be 1.2. This turns out to be minus 0.5. So sum is less than 1, and that process is more likely to be stationary. The formal condition is, of course, this one. Hopefully, you follow this this notation. Okay. In this case, mu is the unconditional mean of AR2 process X. This one. It can be rewritten in this form, the same thing. So here is the sample. Pi 1 is set to 0.9 and pi 2 is set to minus 0.5. So adding 2, 0.4, which is less than 1. So first condition is met. It is more likely to be stationary, and in fact, it is stationary series. AR2 process, by just looking at it, you can't tell, concretely whether it is that. But let's take a look at this one first. Partial order correlation. At lag 1, it's positive. Lag 2, negative. Lying outside this band, the band was 0 plus minus 2 times 1 over square root t. So 2 standard deviation band away from 0, which is null hypothesis. Okay. Where does this number came from? It's a theoretical standard deviation or partial correlation at all lags, right? That's what we covered. So if you look at this band and numbers, 2 are significantly different from 0. That's what I'm omitting. The third one, fourth one, all statistically 0. Whereas, very difficult to tell, but this is one example of tapering off feature of AR process. Here, the lag 1, lag 2, 3, 4, 5, right? So it's like moving this way. Very difficult to tell, only your experience will tell you, but basically it says this kind of curve, tapering off for this particular process. Okay. Of course, if you have more lags, it's fine, right? So before we move to moving average process, let's take a look at real example where I disputed previously. Here, this CT and YT this is a real consumption, and this is a real domestic product, gross domestic product. So this is GDP sequence quarterly, and this is consumption sequence, total expenditure, consumption expenditure. And starting from the first quarter of 1990 up to fourth quarter of, I believe it's 2012. But let me quickly check. Starting from here to actually third quarter. Okay. Now, before you try to build a time series model, the first thing is, of course, to look at some statistic. So let's say here, GDP growth rate. I calculated this one previously. Let's see. So this is what I did using series command. I defined GDP growth rate as 100 times. D log means that's a Gibbs function. It's taking log difference. So you calculate quarterly growth rate. So D log YT means natural log of YT minus natural log of YT minus 1. So one quarter growth rate, of course, approximate number, and made it percent, expressed it in percent. Of course, when you actually talk about GDP growth rate, we use simple growth rate. So YT minus 1 divided by YT minus 1. That's simple growth rate, right? But that is approximated as log difference, right? But sometimes in finance, we prefer using log difference instead of simple growth rate. In this case, we call it continuously compounded return. So if stock return is calculated in this way, if this is stock price, and this is going to be stock return, and if you take this one as a log difference, we call this return as a continuously compounded return. And continuous compounded return is usually the return sequence we usually work with in finance literature. Okay? So that's one. Because we take this log difference, the first one is going to be missing, right? The second one is the first observation. Okay. We know that this is, of course, stationary. Looking more like this one, right? Now, let's say view here, correlogram. It says level. That means you are working with this one, just growth rate, this sequence. Okay, so what do we got? Partial correlation is lying outside this band, right? So this is significantly different from 0. Applying 2 standard deviation band, which is usually about 95% Thompson's band. Have you noticed these two numbers are the same? Is this a buck? So pi 1, 1 and rho 1 is the same at k equals 1. It's correct. At lag 1, these two numbers are the same. But other lags are different, right? So theoretically, rho 1 and pi 1, 1 are the same. Theoretically. We can show that. Okay, what else? Well, partial correlation at other lags are all 0. Okay. Autocorrelation, of course, is all 0, but it appears that there is a little slight pattern like this one, although small. Right? So to me, it looked like it cut off here and taper off here. But later, we'll have to decide whether, in fact, this is AR1 is preferred or the other alternative model is preferred using other approach. But let's stick to the information we have up to now. So more distinctive cutoff feature here. So our best guess at this point is AR1 process. Okay, AR1 process for GDP growth rate. What else here? Q-stat. Q-stat. Well, Q-stat is looking at this number, which is very small, right? It's like this number squared, still very small number, right? But when you multiply that by sample size, you will get this number. So blowing up. Okay? This number, for instance, this number, square this plus square that, and then add this, and then times number of observation t. So Q-stat is defined as sample size times summation of this squared. So for this number, these two square terms added. For this one, 3 square term. This one, and all scaled by sample size t. Right? Why do that? Why do we do that? Well, basically, it is known that this quantity under null hypothesis, which is no serial correlation whatsoever, under null hypothesis, it is distributed chi-squared distribution with 1 degree of freedom, this quantity. On the null hypothesis, this Q statistic is distributed chi-squared with degree of freedom 2 degrees of freedom. And these p-values you guys know that probability in E-views. Chi-square distribution, let's say with degree of freedom 1, would look like this. It's all positive. So chi-square random variable lie to this direction only. There's no negative. Right? What is, well, it has longer right tail. It is not symmetric. Okay. Expected value is about there, which is 1. So degree of freedom is expected value of chi-square distribution. So chi-square 2 degree of freedom, 2 degrees of freedom will lie to that direction. Flat, and gets more of a symmetric distribution as degree of freedom increases. Okay. Now, whenever you see some statistic, let's say Q stat is no exception. Let's say 11.209. So 11.209 here. So this is statistic. Always, statistics are derived under the null hypothesis. So what is the null hypothesis of this number? No serial correlation. So whether this is 0. No serial correlation. Okay? And what mathematical statisticians or econometricians do, they derive this distribution, theoretical distribution of this kind of statistics under the null hypothesis. Okay? So someone derived that show that this statistic is distributed this under the null hypothesis. So we calculate this quantity as sample size times rho 1 hat squared. Turned out to be this number. And now the p-value there before this number. So if your sample statistic lie away from this region, that means there is not much evidence supporting null hypothesis. Right? It turns out to be, well, if this all area is 1, it says 0.001. This area is 0.001, where this whole area is 1. So very unlikely that null hypothesis holds. So null hypothesis is strongly rejected So it says this thing is a real thing, not zero, according to this statistic and p-value. What this number tells you is this and that number, these two numbers, at the same time, jointly, these two serial correlations are non-zero. It says, yes. Why? Well, this appears to be individually zero, right? Appears to be zero. But combined, this one is still strongly positive, right? So this effect lasts. But when it comes to this region, then the effect of this one diminishes, and then p-values start rising. So when you, for instance, estimated regression, and then you can calculate fitted residual, treat this sequence as just series. You can calculate that Q statistic to see if whether there is any serial correlation left. Okay. So before I let you go, well, after checking this one, because this is the simple context, no complication here. So what I can show you is, let's say, here quick estimate equation, GDP, GR, that's the growth rate. C, AR1 process. It says estimation method least square, right? And whole sample. We don't have last observation and the first observation either, right? Then it will automatically ignore that part. So it says our GDP growth rate in the simplest analysis, we have sample, it says adjusted. We lost first quarter observation to calculate growth rate, right? And also we have AR1 model fitting. So XT, T minus 1. So lagging one, so we lose another one. So we start from quarter 3 up to quarter 3 of 2012. AR1 coefficient, this is mu. So overall, 1.24% growth rate over 2 decades. That's what this initial result suggests. And the variation is explained by previous observations, about 11%. So you can be happy with this and try to hopefully use other feature of this software to generate forecast. Or before you move to that part, you can do some more. Okay, so when we come back to this problem later, we see that, well, our data is a little peculiar because of a couple of big crises marked permanent mark on GDP sequence. Right? So we have to handle those part in somehow. So we'll get to that part. But this is the simplest forecasting model, AR1 model, is using or by examining sample statistic like sample correlation function and sample partial autocorrelation function. Okay. So this is what I have to say for the day. I believe time is up. Before I stop, any questions?